Hello and welcome to the Erlang Solutions monthly webinar. My name is Mladen Milicic and I'm the Solutions Director here at Erlang Solutions. Today's webinar represents a continuation of a series of webinars we are organizing across topics of interest in the world of Erlang and dealing with solutions based on the Erlang programming language. Our topic today will be dealing with one of the most significant areas of implementation of Erlang-based solutions with deep real-world impact on the financial services industry and related sectors, and also on how we live our daily lives and how we depend on advanced and sophisticated monetary transaction services that we have come to see as commonplace. The story of Erlang in finance and the next generation of automated payment systems will be told with the backdrop of practical implementations Erlang Solutions have performed, as well as through a testimonial by our guest company, Tutuca, who operate as an issuer of prepaid debit cards. As with any live event, please excuse any technical issues we may encounter today. To start by telling you a bit about Erlang Solutions, we are a products and services orientated company completely devoted to the Erlang programming language. Since our founding in 1998, we have worked with organizations and individuals using Erlang, helping evolve the language and supporting people and businesses using it. Today we have about 80 people across our offices in London, Stockholm, Krakow and Budapest, and working on projects across the globe. We promote the Erlang cause and are keen on creating value and competitive advantage for our customers across industries and through the unique features and characteristics of Erlang as a language. We are ambitious in development of Erlang-based products and we work to create lasting partnerships with our customers. Now, I'm really pleased to say we have two speakers joining us today and whom we have carefully selected as best invited to tell you about Erlang-based payment systems. Firstly, my colleague and the Erlang Solutions Senior Architect, Rudolph Van Graan, will start us off with a technical overview of Erlang in financial systems, financial transaction processing, and financial switching. Rudolph has spent many years working on and with financial switching platforms and has led a number of projects delivering key infrastructural solutions in payment processing. Now, of course, Erlang characteristics sound unrivaled on paper, but ultimately the proof of the capabilities of Erlang-based payment systems must surely lie in their practical implementations to date. This is why I'm pleased to say that our second speaker today will be Shaun Hodgkiss, the Technical Director at Tutuca. Having run Erlang-based payment systems in business practice for years, Shaun will be in a very good position to share the intricacies, the pros and the cons of living with such platforms on a daily basis. Please allow me to finish by saying you are welcome to post questions throughout the duration of the webinar by using the chat facility. Our speakers, Rudolph and Shaun, will then answer as many questions as time allows at the end of the webinar. If any questions do go unanswered, you are welcome to raise them via email using the following address: webinar@erlang-solutions.com. That's webinar@erlang-solutions.com. If you're interested in learning more about Erlang-based payment systems or simply wish to establish whether they may be a solution for the challenges your own business may be facing, then please feel free to get in touch. Contact me directly. My email address will be displayed in one of the final slides of the presentation we will share with you today. The same goes for any other questions you might have. Feel free to contact us. I would now like to hand over to Rudolph Van Graan, who will be glad to start us off.
Hello everyone, this is Rudolph speaking. As Mladen said, I've been working with Erlang for a very long time, so I think at present I'm almost at 14 years. I've spent most of those 14 years as a director and co-founder of a company in South Africa called Patmatch Technologies. But in the last 2 years, I've been doing a lot of work outside that, specifically in Erlang-based payment systems. So my experience started very early. I think it was in 2004 or so, where our very first customer was Tutuca, and they presented us with a very interesting challenge, which we're going to tell you about a little bit about the work we did today. And then in the last year or so, I've been working as a payments architect for a prominent UK company, and we've built and are currently deploying a major payment system in the Far East. So my presentation today, I'm going to cover 4 different areas. So first, we're going to start off with just talking about the two systems I just mentioned, and then I'm going to move over to a little bit and talk about what transaction processing is and where that fits in. And then you will hear me mention the notion of a financial switch a few times in this presentation. So I'll just cover off what it is, what is a financial switch, and then finally, I just want to dig into a little bit more technical details and show you what the messages look like that these switches process, and that's about the ISO 8583 standards. So in our experience, as I said, we started off with Tutuca. Now, they approached us in my previous company and asked us to design a solution to connect their existing voucher system to a financial switch using ISO 8583. Now, over the years, we built up that simple gateway into a fully fledged financial switch that connected to various customers. And this project is what started off my enthusiasm for financial transaction processing. Now, I'm going to discuss two different types of payment systems. Now, with Tutuca, we're talking about a card processing system. So a card processing system in the sense that anytime you use your debit card or credit card at a shop or ATM, that card information is captured from that card, and it's then passed through the financial networks to your bank, and that's done in order to take a payment from you as person and to pay the merchant. So the Tutuca system sits on the one extreme of the payment system's scope. It's what we call an issuer system, so issue of a card, in other words, a payment card. And this is what Tutuca does. They've built all the infrastructure to issue prepaid debit cards. Prepaid in the sense that someone has to deposit funds onto the card. So you load money in a certain way, and then those funds are used for payments. Now, Tutuca system uses ISO 8583. I see there's a typo on my slide. Messages for interacting with the financial networks. Now, there's a lot of cryptographic stuff in the system, and for that we used interfaces to what we call a hardware security module, and we built a native Erlang interface for that. So just on a very high level, the system stack consists of 3 levels. So at the very bottom, there's a Microsoft SQL Server database that stores completed transactions and keeps track of all the balances and helps with reporting. And then there's a treasury, which is where Shaun comes in. He'll tell you a little bit about that, which is essentially where the money is kept and tracked. And then at the top, there's an Erlang payment switch, which handles the security, the connectivity to the payment networks, and manages the messages. So at this stage, I'm going to hand over to Shaun, and he's going to tell you a little bit about their system. Thank you.
Hi, everybody. This is Shaun speaking. Thanks very much for the introduction so far. Well, as has been mentioned, I'm the technical director at Tutuca. Yes, we had a quirky .com domain name all the way back in 1999, long before it was trendy. But based in South Africa, we actually chose the name because it's a Zulu word for growth or progress. So to be fair, there's a bit more meaning to our name than just having run out of vowels. We see ourselves as a technology company that builds software to power prepaid accounts. These prepaid accounts can take any form, which would typically be a credit card, and that's what we'll focus on today, but could in fact be any token, from a printed voucher to a text message code, for example. Our most recent claim to fame is winning the best prepaid processor in Central Europe, Africa and Middle East at the Global Prepaid Awards, which we won from microlending card program that we power with MasterCard. We've been a third-party processor for MasterCard since 2005 and a Visa third-party processor since 2010, where we were quite proud to have our first card with them be the official FIFA World Cup 2010 South Africa Visa card. If I have a dig in the database, I can see that we've got about 20 million active accounts, and on average, we process about 50,000 transactions each day. Although obviously this fluctuates quite wildly by the day of the month as well as the month of the year. But getting all these transactions to our core account system is an Erlang switch, which we've been running in various iterations for pretty much the past 10 years. Now that you have an idea of who we are, let me give you a better idea of where we sit in the transaction processing world. Then I can give you a close-up look of where Erlang sits within our environment. So looking first at the typical transaction flow for a MasterCard or Visa credit card, you can see it originates, as you would expect, at a merchant. The terminal or the POS device of the merchant will switch the transaction through their acquiring institutions until the transaction reaches either the MasterCard or Visa network, depending on which brand is associated with the card. And then from their respective networks, Visa and MasterCard are able to identify us, Tutuca, as the processor for that card based on the first 6 digits of the card number, which is known as the BIN. Then we have within our data center vault a device from MasterCard, which is known as a MIP, and a similar device from Visa, known as a DEX. And these are basically the last mile connections to which we connect using our Erlang switch. And the Erlang switch and the rest of the system obviously falls within our own environments. So if we take a closer look at what's within our own environment and how all the elements are connected, you can see we've created for redundancy at every level. The arrows pointing everywhere. You'll see that the MIP and DEX devices are listed again on the left. And looking at them in more detail, we actually have multiple MIP and DEX devices. Then our network is segmented into multiple zones. And one of the most interest is what we have very imaginatively called switch zone, since it's the zone that performs switching. This zone contains multiple servers running the Erlang switch software, together with our hardware security modules, or the HSMs, which we obviously use for our PIN cryptography. We have our connectivity spread over multiple servers, which in turn connect to multiple HSM devices, and this provides us with redundancy regardless of whether we lose a bank connection or a server or one of the HSM devices. You'll see the diagram also shows a data zone and a web zone. These zones have their own redundancy in place, which I haven't reflected in the diagram because it isn't pertinent to the discussion. But in terms of connectivity, the Erlang switches connect to SQL Server for their own data storage needs. And then they connect to our web zone for their primary responsibility, which is the actual posting of the translated ISO 8583 financial transactions to our core account system. So now that you have an idea of how we make use of Erlang and where it fits into our environment, you might wonder how we ended up with an Erlang system. As is often the case, and despite us being a technology company, we weren't interested in any specific language. Rather, we just knew we needed an ISO 8583 online transaction processing switch, which had the usual simple OLTP requirements, handling multiple incoming transactions at once, and being able to scale up as our transaction volumes increased. While, of course, at the same time being 100% reliable and fault-tolerant if any problems do occur. As you saw on the previous screen, there are lots of systems and interdependencies in processing any transaction, and it was imperative that the switch not be a new point of failure. So our research for ISO 8583 skills is what led us to Pattern Match Technologies, which was run at the time by Rudolph. And he, of course, just happened to be an Erlang evangelist, and at least according to his assurances at the time, Erlang happened to fulfill our requirements. And fortunately, as it turns out, Rudolph just happened to be correct. Interestingly, I suspect that rarer technical skills, such as ISO 8583 transaction switching and PIN cryptography, are more often found in the same habitat as Erlang developers, rather than, for example, PHP programmers. So in hindsight, it seems a natural alliance. Skip forward 10 years, and our Erlang switch software continues to process increasing transaction volumes without fail. Pattern Match Technologies in South Africa, they continue to develop our regular new feature requests that allow us to meet our growing needs. And we're fortunate to have Rudolph still provide ISO 8583 and Erlang consulting from the UK. Some of this new functionality that the product has evolved to provide include catering for the additional ISO 8583 variants that Rudolph mentioned. There's the cryptography and PIN validation on the HSM devices, which we didn't implement until about 2009. Offering multiple cluster-aware connections is something that we are still in progress with. And another project that we're currently busy with is integrating chip transaction processing. In addition to the solution requirements that I mentioned previously, I want to highlight that one of the biggest advantages is the lack of downtime when patching bugs or making small changes. And this is actually something so simple to do that we do it ourselves just using patch files that are provided to us. Even package updates can typically be implemented really quickly and with minimal effort, although we would probably fail over to another server while making a big change. And a final point that may be of interest is that being a Windows house, we originally ran the switch under Windows, and this original Windows version actually continues to run to this day, handling some of our legacy x25 connections, which we haven't translated in the newer versions. We did, however, migrate to Solaris as we became more comfortable with it, and so our newer versions all run on Solaris, which has obviously provided benefit for managing them. That's it for me. Thanks everybody for your time. I'm going to hand back to Rudolph now to continue with his more technical examination of Erlang, but I hope that I've given you some insight into how Erlang has provided Tutuca with an enterprise level payment switch. Thank you.
Thank you, Shaun. I'm just trying to get the presentation back on. Is that working? I just need to check. I guess so. Okay, so that was a card-focused switch. The last 2 years, I've been working on something very different, which was a payment switch. Now, in the UK, there's a service called Faster Payments, which is used when you make a bank-to-bank payment. So, for example, if you log into your internet banking and you select to pay someone directly into their bank account, that payment clears literally within seconds. So the recipient of that payment, or the recipient of funds, would be able to check his bank account, and the funds would be in that bank account within seconds. Now, I was part of a team that was working on a very similar service for the same company that operates that service. But whereas Faster Payments runs on extremely expensive hardware, specifically tandem non-stop hardware, and specialized switching software called Distra, we were challenged to build a system that was going to run on commodity hardware and on Erlang. So instead of having literally millions of pounds of costs, this system was meant to be running on hardware which cost in the order of thousands or tens of thousands of pounds. Now, we built this system again in Erlang, and it also consists of very similar components as the Tutuca system. So there's the Erlang switch, which deals with financial messaging, and then there's an administrative backend, which deals with reporting and settlement. I just want to say something about settlement because I've mentioned it twice now. Settlement is a process that happens between the banks at least once every business day. So essentially what happens is they all add up the payments that they make to each other and that they receive from one another, and then at a specific time during the day, there's a cutoff, and then what happens is the money is moved by the central bank between the different banks. And the switch and its associated administrative backend is responsible for calculating the values of the settlement. Now, for this process, we had to use a different messaging standard, which is not ISO 8583 as for the card payments, but an XML-based payment format called ISO 20022, which is reasonably new, but used for doing interbank payments. We were also, in this case, asked to provide a dual data center operation. So I'll show you in one of my other slides that a traditional system runs active-passive. And this system, they asked us to create an active-active system, which was really, really challenging. So the difference between this system is it's bank to bank, opposed to card holder to merchant, and it's also meant to be part of what in the UK is called national critical infrastructure. Well, that means you can't take it offline and it has to function permanently. So if anything goes wrong, it impacts the national economy. The backend system has similar functionality as the one we created for Tutuca, but in this case, it needs to deal with the messages in XML opposed to the binary format of 8583. And we also had to implement cryptography support. However, in this case, we did not build a native Erlang interface to the HSMs. We built a Java bridge that interfaced with the Java security modules. Now, what is interesting about this system is the fact that it has to operate in 2 data centers at the same time. So logically, the system looks like my diagram on the screen. So you've got a set of switches in each one of the 2 active data centers with a link between the 2 switches that are used to communicate. Now, as the transactions complete, they post it to persistent queues, which we used an off-the-shelf product called RabbitMQ, also built in Erlang for. And then the transactions are dequeued from the administrative backend and persisted into the database. Now we used standard RDBMS again. In this case, it was Oracle. And the admin interface is responsible to calculate the settlement based on the completed transactions. I'll show you in further on in the presentation how we actually calculate the values of the settlement and how there's end-to-end reconciliation in this whole system. Now, active-active operation is a really tricky bit. Imagine that you've got 2 institutions, the one at the top, the one at the bottom, that needs to send a payment to one another. And the one at the bottom's got a connection to 2 data centers, so the red arrow and the white arrow, and the one at the top has only got a connection to the rightmost data center 2. So the problem that we had to solve is that the institution at the bottom can send a message to the first data center, but the second institution is not connected to that data center. So we had to build in an awareness between the switches of who is connected where, and build in a capability to send the message from one data center to another, which will then forward it on to the first institution. Now, there's a very tricky problem that we had to solve here. And one of the functions of the switches is to prevent duplicate payments. Now, if you think about the card payment switch, what essentially happens is when you use your card, the merchant's POS device requests your bank for payment. So it asks, it does a debit on the account. So it asks whether that bank is willing to deduct the funds. So it always reduces the funds on the cardholder side, and then what happens is the merchant receives payment a few days later. But for a payment switch, in this case, the payment is pushed. It's not a pull like in the card switch. So the moment you go into your internet banking and you push the button to send the payment, what will happen is that the funds are deducted from the first institution, and essentially within a few seconds, it's credited to the second institution and your bank account. So if that transaction is for some reason sent twice, you will end up with twice the amount of money in your bank account, and there's nothing that prevents you from spending it. Now, banks want to avoid this at all costs. So what we need to do is to build in specialized logic in the switches to prevent this from happening. That's called the credit risk. So one of the major challenges we had to solve was to build a mechanism that works for protecting the institutions from double credits, and works over 2 data center and active-active operation. Now, we built a solution based on the interswitch link between the 2 switches, and on what we call a duplicate screening function in the switches. Now, we used Manesia and some interesting algorithms to build the logic for preventing double credits. Now, unfortunately, I can't say much more about it. I just thought it would be interesting to share the actual problem with everyone. Now, the question might come up, so why use Erlang for all of these things? Now, I'm not going to go into too much detail, but essentially Erlang is a very, very small and compact language. So there's not a lot of libraries to learn. There's only one or two ways of doing anything. And it's very simple to build quite complicated systems in it. Now, one of the things that's interesting in payments is that because Erlang is a functional language, it makes it very, very easy to build the logic that understands these payment protocols. And I'll show you right at the end of the presentation what ISO 8583 looks like. Now, we managed to build logic and libraries that makes it very easy to connect to the different payment networks. And one of the challenges is that for example, the MasterCard protocols are very, very different from Visa. But we still managed to create abstractions that could handle all these networks without too much code. And then also, obviously the fact that Erlang is made for distributed operations. So the function in the payment switch where we run multiple switches in one data center and we have the distributed database for the duplicate screenings, that functionality is natural in an Erlang system. Now, one of the best things about Erlang is the capability that you have to upgrade code. Now, I think, Shaun, you mentioned about this, and we used to create very small patch files to fix a bug, and then we would just distribute the patch files and load that into the switches while they were operational, and then if we screwed up, we would be able to back them out at a very short notice without taking the switches down. And that's really critical when you need to have almost continuous uptime. Now, obviously, in some cases, it is necessary to do a complete system upgrade. Now, in our experience, we could do that without doing that on the fly by just designing your system in a way where you would have multiple switches and they could take over the load from one another. It's reasonably simple to take one switch offline, upgrade it, bring it back online, and take the second one. But if you've got the resources and you've got the process in place, Erlang is a very, very good platform to do this live on. So you can create procedures and build the mechanisms to do a hot upgrade where you actually replace the entire system's code while it's operating. Now, another aspect of Erlang that's useful in payment systems is the supervision capability. Now, imagine that you've got 5 or 6 or 100 transactions on the fly. Now, in other words, running at that time. You don't want a problem in one transaction to interrupt the other transactions. So we would encounter that, for example, in the Tutuca system. If we, for example, get someone using the card in China and they would include Chinese characters in the merchant names, or we would get some strange runs-in condition somewhere in the network, we would have it that the transaction is actually impacted. But because we structured it in a way and we used Erlang supervision logic, it was only that transaction that was impacted and none of the others. Now, the supervisor, if you can set it up in a way that, suppose it's supervising logic that deals with a database query. Now, if you encounter a transient error and that process dies, the supervisor can, in some cases, restart that process and resume functionality if you've designed it in that way. Now, in some of the systems, in the payment system, we did it exactly that. In other systems, for example, the Tutuca system, due to the nature of ISO 8583, it's not necessary to restart the transaction. The upstream and downstream switches will retransmit messages, and there are very complicated rules for how you deal with that. But the supervision function is very useful for dealing with, for example, database outages or TCP connections that fail or get torn down for whatever reason. Now, I just want to talk about two specific issues we faced. that makes it quite interesting in the payment world. Now, the first thing has to do with decimal support. Now, Erlang does not have support for fixed point decimals. In other words, where you have 10 pounds, 5 pence, where you need to have like fractions and all that. It's only got support for floating point numbers and for integer numbers. Now, if you look at the first red line there, one of the major issues with floats in Erlang is that it's not exact. So, example, I showed you there the case of where you type in 1.001 and you multiply it by 1,000, and then Erlang returned a very surprising result, which is 1,000 dot lots of nines, and you can see that there's a rounding error. Now, because Erlang has that, it works with floating points, you can't rely on that for dealing with money. Now, we had to create a specialized decimal library to deal with this. Now, I've just shown you 3 lines there where we did exactly the same multiplication. And in this case, we got the exact answer. So the first was to convert the floating point number to an accuracy of 3 digits, return the decimal structure. The second one, we assigned it to a variable a. And then in the third line, we multiplied the decimal a with 1,000, and it formatted the end result correctly as 1001. So this is absolutely critical if you want to build financial systems, is to work in decimals and not in floats. And then the second big challenge we faced is a thing called PCI compliance. Now, the audience who works in payment systems will know that this is an absolute nightmare. And it means that you need to implement a lot of procedures in your company, which means you're supposed to have access control to data, you've got to have security policies in place, all sorts of things. But you also need to write your software in a specific way that makes it PCI compliant. Now, PCI compliance, from a software point of view, essentially means that you're not allowed to store any information that can be used to originate a transaction. Now, in a card processing system, the large number on the front of the card is what we call a PAN, a primary account number. Now, if you've got the PAN, in some cases you can already initiate a transaction. Now, there's also a little 3-digit number or sometimes 4-digit number printed on the back. That's called the CVV. It's a security code used to prove that you've got a card. Now, one of the golden rules in payment processing systems is that you're not allowed to put the PAN into a database or log it into a log file. You're not allowed to store the CVV, the 3-digit code at the back, in any way. And you're supposed to use cryptographic hardware to validate the CVVs. Now, the rule here is it has to be done in hardware. So you cannot use, for example, Erlang's crypto module. So even though it's got support for some of the operations you need for payment processing, it's a complete no-no. Now that means we've got to build HSM support, hardware security module support, into our systems. And we had to do that in both of the systems. So in Tutuca's case, we built a direct Erlang interface, which used TCP/IP to communicate with the hardware security module. And in the payment system case, we went via a Java driver, which did essentially the same. Now, the purpose of this whole thing is to store the keys. Now, in Tutuca's case, there are lots of keys. There's, for example, a key that's used to derive the PIN codes, the PIN codes that you, when you apply for a debit card, and the issuer would mail you the PIN code to that debit card in a secure envelope. Now, that PIN code is generated by the hardware security module, and there are various ways in which you validate it. So we had to do that, and we managed to build all of these things in Erlang using the HSM, and it was quite tricky, but I think it worked really well. Now, I just want to now move on to my transaction processing section. just talk about these things that the switches do, the transactions. Now, the most fundamental thing is a transaction is about buying and selling. So if I as a person wants to buy coffee from a second person, he would give me the coffee and I would give him my $10 payment if it's that expensive. So it's about paying someone for goods and exchange of value, my cash in exchange for your cup of coffee. Now, this was done in cash. Now, in the last 40 years or so, these things have started getting electronic, and now that's essentially the only way in which you can buy things. So what is a transaction? Well, if you think about it in a very simplistic way, it is the act of entering transactions details into the accounting systems by all the parties involved. So if I'm making a payment from my bank account, my bank would record that you've made the payment, 10 Rand, $10, and the merchant's bank would record that he's receiving $10 payment. So the one deducts, and the one debits, the other one credits. And then at the end of the settlement period, each one of these banks have an account at another bank, usually the central bank, and they would move that $10 from the one bank to the other bank's account, which is exactly the same thing. So the switches are responsible for coordinating the entries into all the accounting systems. So what is a transaction switch? And what is transaction switching? So it's essentially the process of agreeing that a transaction has happened or that can happen, and then the whole collaboration of entering the data and settling everything after that. Now, the switch itself is responsible to keep track of all the transactions that are in progress. Now, because there are messages involved, and I'll show you in a while what one of these messages, the sequences look like, the switch needs to track which transactions are running and what the state is. So, for example, if a transaction is not completed properly, it has a procedure for coordinating what we call backing out the transaction or reversing it. For example, if you receive the same message more than once, you need to take action, and then if a transaction is approved, or it captures that and send it off for settlement. And then there's also a function of routing the messages between the different connections. So I'll show you that one switch would usually have connections to lots of different entities. And one of its primary purposes is to look at the message and decide where I need to forward it to. And all of this has to happen continuously and concurrently. Now, switches can be connected, like my diagram shows you there. So it can be connected directly to a bank or an issuer system like the Tutuca system, or it could be connected to another switch, which could be the MasterCard MIP, which in turn is connected to another one, and eventually connected to a bank. Now, it receives, formats, and routes financial messages. So it ensures that the transaction is captured consistently, and it works in tandem with other switches. Now, inside the switch, there are a few different components. So in the case of the Tutuca switch, there's a component that deals with formatting the different messages that you receive from the institutions in a concise format. So for example, if the Tutuca system is on the right, the system that I've shown as Treasury, the switch would convert the messages from variant 1 and variant 2 into the single format. Now, that's already quite a significant job, and you need to study MasterCard and Visa documentation that are thousands and thousands of pages long in order to work out how those translations need to happen. And it then needs to look after the security of the messages. Now, inside the switch, we've got a component that we call endpoints. Now, endpoint is essentially a logical component, and it connects to a specific institution. So if we've got a connection to MasterCard, we would create at least one endpoint that talks to MasterCard and that runs the MasterCard variant. We'd have another one for Visa, and so on. Now, routing is essentially a set of database tables that tells you that if you receive a a primary account number with this bin, the prefix is first 6 digits, then send it on to that system or do the following with it. There's also a subsystem in there called store and forward, which deals with failure cases. So for example, if the issuer system is offline or it doesn't respond quickly enough, MasterCard would send you a message that says, we have declined the transaction, please reverse whatever it is you've done in your treasury. And the store and forward subsystem is responsible for taking that message and delivering it regardless of how long that takes. You can have limit logic, which has to do with, for example, preventing someone from making more than 4 or 10 transactions a day. That's primarily for fraud preventing purposes. You would have the accounting reconciliation subsystem, which I'll talk about in a short while. Security, which deals with checking that messages are valid, so that the person or the entity that sent them usually signs these messages, digital signatures, and the security system would check that these things are valid. And then the duplicate prevention logic that I've already discussed, and then it connects onto RDBMS and HSM's hardware security modules. Now, reconciliation is a very, very important process in the switch. Now, imagine we've got 3 different financial institutions, and during the day, each one of them sends messages back and forth that results in debits and credits to accounts. So credit if you receive money, debit if you send money. Now, the switch maintains a set of reconciliation totals for every, what we call a reconciliation period. So I've used the numbers 89 and 90 to indicate this. So every time that the switch sends a debit to a financial institution or credit to a financial institution, it increments those values. And then if you add all of them up, in the end, the debits should match the credits. If they don't, you've got a bug or you've got a stuck message or something like that. Now, this is the way in which you ensure that all transactions are always captured. So you can easily detect that there are missing transactions or transactions that have not been captured by checking the reconciliation totals. Now, the reconciliation totals are maintained in lots of different places. Every financial institution maintains his own set. The switch maintains one for all the internal components. It maintains additional totals for each institution it's connected to, and it's also forwarded to the backend systems for checking that all the transactions been received, that's been pushed into the queues for capturing. So this is really, really important. Obviously, it's not as simplistic as I've shown you here. You need to keep track of the number of transactions. You keep track of how many have been reversed. There's also multi-currency issues involved. There are issues with synchronizing the different accounting periods. But that's all functionality built into a switch. Now, one of the interesting problems that switch and payment companies need to consider is disaster recovery. So I've already discussed the active-active topology that we used on, or that we built in the payment system. But in a traditional system, it's normal to run in a primary and a disaster recovery topology. So you would have your switch, a single switch running in the primary data center, and all the transactions would be sent there. And then if something would go wrong with that data center, you would have an outage or power failure. There would be a procedure that you'd invoke, and you would switch over to the secondary data center, the disaster recovery site, and boot up the standby switch. Now, in order to do this, you typically need to migrate and replicate your databases from primary to secondary. Now, fortunately, the switch has only got 2 types of data it needs to replicate. Obviously, configuration is one, and the second one is the information dealing with transactions that are in flight or just completed. So in a system like Tutuca, what we would do is we would have a database set up, for example, Microsoft SQL Server, and we would do the replication based on the database. But in the payment system, we had the inter-site link to do this in real time. So this is one area that when you build a payment switch that you need to think about very, very carefully. So I'm going to move on to the last section of my presentation, and this is to do with looking at actual messages that flows in a card payment system. So this is the typical messages we'd see in Tutuca system. So ISO 8583 is used for card payments. So this is the protocol that's used when you interact with an ATM, an automated teller machine, withdraw cash, or when you make a payment in a shop or restaurant. Now ISO 8583 has got 4 major classes of messages, so it's groups of messages. The first one is to do with authorization. So authorization is what happens when you make a payment. So as soon as so the merchant would go into the point of sale device, he would enter the amount of the payment, he would ask you to swipe your card, you would enter your PIN, and then the POS device would send an authorization request to the payment system. So that would usually end up in the MasterCard or Visa networks, and Visa and MasterCard would then forward it on to someone like Tutuca, and it would get into the payment switch, in this case the Erlang switch. Tutuca would open up the message and decide whether that cardholder's got enough funds for that payment, and then either approve or disapprove it. Presentment is about banking the funds, moving the funds. The presentment messages are used when you withdraw cash in an ATM. So you can imagine you already get the cash immediately, so that money has to be taken off your bank account immediately. And then there's reversal messages, which has to do when things don't work out. So for example, if the Tutuca would take too long to respond, the reversal messages would kick in. And then there's a 4th class, which are to do with inquiries. So these messages are used generally when you do a balance inquiry at an ATM and so on. Now, an ISO 8583 message consists of 3 major areas, or it carries 3 types of data. First is the type, which is a 4-digit integer number, which indicates whether it's an authorization or a presentment. And then there's a thing called a bitmap. So it's a 64 or 128-bit binary structure that has a flag that indicates the presence of specific data elements. So for example, the number on the front of the card is called data element 2, card number. And so the bit 2, if that's set, DE2 is present, and so on for data element 4, which would be the amount, and for magstripe cards, data element 52. So the switch needs to understand these formats, and what makes it really hard is that this differs. It's almost guaranteed to be different for every type of switch or payment institution you connect to. So the switch has to understand all these different messages. Now, I'm not going to show you a binary message, but this is what a decoded binary message looks like. So you can see on the top left there's a thing called an MTI, and it says 100. So that's code for, this is an authorization request. And then in the middle, you can see all the data elements, DE2, 3, 4, 7, and so on till DE63. And then to the right of that is the values of the data elements. Now the first one, DE2, the card number, you'll see that it's been masked out in the middle. So it's not a complete PAN number. That is where PCI compliance comes into play. It's necessary to do that because we're not allowed to show these messages or the PAN numbers to anyone, and it can't be recorded. So the switch hides the full card number. Data element 43 is also interesting because that contains the name and the location of the merchant. So if you see a name on your credit card statement, that name for that merchant is transported in data element 43 in the MasterCard specification. And then on data element 4, there's an amount. You can see right at the end there's a 200. That is that would represent an amount of £2. So this is what the messages look like, and they are a vast number of these things that you need to understand, and there are rules for dealing with each one of them. So this 100 message would be sent from the merchant all the way to Tutuca's system, and Tutuca would receive this, look up that card number in data element 2, check if there's at least £2 of funds available. If it is, it would reserve the funds and then send it all the way back, responding with a 110 message. So that looks a little bit like the following diagram. So I'm not going to go through the whole thing, but you can see on the left here that the merchant entered in a transaction of $10. The point of sale device would then interact with the card holder asking for PIN, send through a 100 message to the acquiring bank, forwards it to a switch, to another switch. Would end up at the issuing bank, or in this case, Tutuca. Tutuca would do the check for the $10, and it would reserve it, and then send 110 message all the way back. And when the point of sale device gets that 110 message, receives it, it would then print out the receipt. Now the money's not moved yet. So this is the first step in the process. So by the end of that day, or maybe even 2 or 3 days later, the merchant would go into the point of sale device and he would press a button that says, I'm now banking this money. I'm sending it for settlement. And then there's an entire new set of messages that flows from the point of sale systems back to Tutuca that actually completes the transaction, and that triggers the settlement process. So there are, in some of these specifications, there are many dozens, sometimes almost 100 messages that you need to support in the switches, and that makes this a very, very interesting problem to solve. So that brings me to the end of the formal presentation. So I'm going to hand over to Mladen now. His email address is on the screen now, and then I think we're going to take a few questions. Thank you.
Thank you, Rudolph. Thank you, Shaun. And I'm sure everyone will join me in thanking you for a very inspiring talk on Erlang in finance, and obviously in regards to next generation payment systems. Now, I'm glad to say that we have received a lot of questions during the two respective talks, and judging by the time we have available, I can already see that we will not be able to sort of address all of them, but we'll certainly try and provide a couple of answers. One of the interesting questions that has just arrived is concerning PCI compliance and disaster recovery. And the question is effectively asking, with the restrictions on storing PANs, how can one ensure that split transactions actually survive a disaster? So I guess either Rudolph or Shaun can address this. Once again, the question is, with restrictions on storing PANs, how can you actually ensure that split transactions will survive a disaster?
This is Shaun speaking. Sorry to cut you off, Rudolph. I was just going to start off by saying that as an issuer, which obviously Tutuca is, we have a necessity to store the full card number. But PCI compliance obviously ensures that we store those encrypted, and they aren't actually in the switch itself, but stored completely separately as part of the core accounting system. Only the systems that form all the switches in between are not allowed to store the card details at all. And we need the card numbers, though, to actually match that transaction that we receive up to the account that needs to have the funds debited from it.
I can also say something. I forgot to cover that in my presentation. There's a technique called tokenization, where you can substitute the PAN that's printed on the card for another placeholder number and use that in your databases. So if you have a way, usually that's done through cryptography, you can do a translation from a PAN number that's not valid, so a token, to a real PAN number. And that's essentially the accepted way of dealing with that. So you would translate this number into something which is not usable for payment. So it's not enroutable, and that's how you do that. So tokenization is the answer.
Thank you, Shaun, and thank you, Rudolph. One of the questions that have just arrived is quite interesting, and coming from Hector. Hector is asking, do any of the solutions we've discussed support ATM or ABM?
Okay, this is Rudolph. ATM can mean two things. The one, ATM is a communications protocol, but it can also mean automated teller machine. So I'm assuming this is automated teller machine that you're referring to, Hector. And in the case of the card payment switch, yes, ATM transactions are very much part of your day-to-day operation. And that's one of the first things we've implemented in 2004, 2005. It's slightly different from a card processing using the 100 message sequence that I showed you, in that the clearing of the transaction happens essentially immediately.
Excellent. Well, thank you, Rudolph. Another question that I'd really like us to sort of try and address coming from Michael. Michael is asking, a lot is said about Erlang capability to run updates without downtime. Now, he's specifically asking how true is that in real-world business practice? So how realistic is this capability of Erlang to run updates without downtime? In other words, to perform hot code loading?
Okay, I'll take that. Like I said, it's very easy to do small updates. You don't have to do a lot of testing. So we typically deploy one patch file at a time. But as soon as you do something more significantly in Erlang, so where you want to deploy an entire distribution, a whole system at once, I would recommend that you do a lot of testing before you do that. So you would typically test that your upgrade works properly. And you would spend a lot of time doing that before you would do it in operation. So in telecom systems, the hot upgrade of systems are used essentially all the time, but it's because they test extensively. In my experience, it is sometimes easier to design the system that it's not stateful in the way that I've showed you with the payment system, so that it's easier to take one switch offline, upgrade it while it's offline, bring it back online, and state is migrated, than to try and do a hot code upgrade.
And just sorry to reiterate something I previously mentioned, in terms of just small bug fixes, is actually something that we, as essentially the client of the system, do on a regular basis. So we'll receive just a small patch file from whoever's providing it, and implement it in real time, just without taking the system down at all. And obviously you would monitor it carefully after that to ensure that it hasn't broken anything, roll back if necessary. But assuming that there were no further problems, you wouldn't notice the impact whatsoever.
Thank you for that, Rudolph. And Shaun, one final question we can accommodate is an observation and a question. So Sheena is saying Erlang is massively concurrent, but also known as a slower language. So can the concurrency of Erlang make up for its lack of speed in high-frequency trading environments where extreme speed is pivotal?
Well, I'll take that one. That's not okay. In a high-speed trading, which is something very different from what we've discussed, latency is more important. It's not speed. So there are numerous sources of latency in systems, and you would have to deal with that. For example, if you've got a slow network that adds 100 or 200 milliseconds of latency to your system, you will have to deal with that. Erlang is not going to be your bottleneck. But when you get to like nano and microsecond latencies, you should be able to do that in Erlang if your hardware is fast enough, and I wouldn't worry about that. We've had a few customers that's actually using Erlang for high frequency trading, and yes, they had to work hard to get it to perform, but it was capable of doing that. But that's no different from any other language.
Thank you. Thank you, Rudolph, and thank you, Shaun. We've had a fantastic talk, and the time has sort of run out on us. There's many more questions to address, and we will commit to answer all of these questions and send you an email response to everyone who sort of hasn't specifically had their question answered. Now, to sort of close off the webinar, again, please join me in thanking Rudolph and Shaun for a very inspiring talk. Many thanks to all of you who have joined us for the webinar. Please join us again on September 17th for our next webinar, which will be dealing with the React Distributed Key Value Data Store. You will have a chance to hear about the superb scalability, the high availability, and the fault tolerance of React, as well as how easy it is to start using it. On that occasion, I'm really glad to say that we will have with us Alex Fock, the Technical Director and Systems Architect at Google Communications. as well as Rune Skov-Larsen, a senior consultant from Trifork, where Alex will be speaking specifically about how React can perform from the perspective of its daily usage in Uvu's business practice, and where Rune will address the topic from the point of view of deploying React across customers, projects, and use cases. Now, following today, we will be sending you a short survey to make sure we capture your feedback of today's webinar. Please note that the recording of this webinar and the presentation that was shared today will also be available for you to collect on Erlang Solutions' corporate website at www.erlang-solutions.com. Thank you once again, and we look forward to seeing you on our next webinar.